Hello, my name is Win Curry, and I am the project engineer for the Precision High Altitude Sonobuoy Emplacement Program here at SeaLandAir Technologies. I will be talking about this technology, which was originally funded under Small Business Innovation Research Topic N68335-22-C-0040. The Precision High Altitude Sonobuoy Emplacement, also called phase, is essentially a one-for-one swap of the existing descent module of an A-size sonobuoy, enabling rapid deployment of sonobuoys with decreased time to splash and increased accuracy. With initial investigations beginning in 2008, phase has seen numerous cycles of development and is expected to achieve technology readiness level 9 by the end of the current contract. Before we jump into the details of the technology though, I'd like to first introduce you to our company, SeaLandAir Technologies. Located in Jackson, Michigan, SeaLandAir employs nearly 60 people with a mix of engineers, lab technicians, project managers, and other staff. Founded more than 25 years ago, SeaLandAir has developed expertise in early to mature stage applied research and development. We particularly specialize in the areas of small unmanned sensors and vehicles. In that time, SeaLandAir has executed several Phase 1, 2, and 3 small business innovation research efforts. We've also executed many other transactional authority, future naval capability, and rapid innovation funding contracts. All of this experience has contributed to SeaLandAire's reputation for solving challenging problems and enabling the collection of data from difficult environments. Our mechanical, electrical, transducer, and systems engineering teams work cross-functionally on the wide range of our projects, and our lab technicians are aligned under these engineering disciplines to support the building and testing of our solutions. So now that you know a little about SeaLandAir and our capabilities, let's discuss the Navy challenge. Where is the opportunity for improvement to allow our naval forces to perform even better? For some time now, the Navy has deployed sonobuoys from maritime patrol aircraft, also called multi-mission aircraft, or MMAs. These MMAs benefit by maximizing time spent at a high cruising altitude, both in terms of fuel and airframe longevity. Current production sonobuoys descend from their release point at a fixed rate. Therefore, as the altitude of release point increases, so does the time it takes for the sonobuoy to reach the water. This time is also known as time to splash. In parallel with this, as the sonobuoy spends more time in the air, it is more exposed to various winds, which would cause it to translate from its intended drop location. Therefore, when the sonobuoy is dropped from high altitude, it will not only take longer to reach the water, but it will also be more inaccurate. While there are steps that can be taken by the aircraft to minimize these issues, the most ideal solution is to improve the sonobuoy itself, such that it will be able to independently minimize the consequences of high altitude sonobuoy deployments. Now, what is the solution to this challenge? Phase. Now, to date, phase airdrop testing has validated significant improvement in time to splash and accuracy. From 15,000 foot altitude, phase-equipped heavy sonobuoys are seeing 50% reduction in time to splash, while light sonobuoys are seeing 40% reduction in time to splash compared to that of their legacy vintage. As discussed earlier, a consequence of reaching the water quicker is that the sonobuoys can also be dropped more accurately. From 7,000 foot altitude, we have seen 39 meter circular error probability for heavy sonobuoys and 21 meter circular error probability for light sonobuoys. This means that when a certain number of sonobuoys are dropped from 7,000 feet and aimed at a position of importance, 50% of those buoys will be within 39 meters or 21 meters of that target. So what platforms are meant to benefit from this system? Well, currently, it is meant to benefit the AN/SSQ-62 and AN/SSQ-53 sonobuoys, also called die-cast and die-far sonobuoys respectively, as they have been identified as the platforms of highest priority to benefit from phase. However, we at SeaLandAir believe it could be modified for other sonobuoys and/or any parachute-based air deployable system in which time to splash or placement accuracy is critical. Beyond the benefits provided to the mission objective, phase also provides benefit to the multi-mission aircraft itself, allowing the aircraft to remain at cruising altitude during sonobuoy deployment missions, reducing stresses on the airframe and prolonging the life of the aircraft overall. Since the inception of phase, 3 key performance objectives have remained the focus of the SeaLandAir development team: safe separation from the aircraft, stable high velocity descent, and a safe water impact. To accomplish these objectives, phase utilizes a parachute staging system, which is described in the graphic on the right. Upon release from the aircraft, a phase-equipped sonobuoy behaves identically to a legacy sonobuoy. The wind blade ejects and the parachute deploys, allowing the sonobuoy to horizontally decelerate and stabilize before beginning its vertical descent. After the sonobuoy stabilizes, though, phase-equipped sonobuoys and legacy sonobuoys behave differently, as the parachute is then reefed by extending 2 of the 4 parachute shroud lines, turning a once-to-billow parachute into a streamer. This significantly reduces the drag in the system, allowing the sonobuoy to fall at a much higher speed. Once the sonobuoy reaches a prescribed altitude, the other two shroud lines extend, causing the parachute to reinflate, which decelerates the sonobuoy, allowing it to safely splash into the water. In order to facilitate these transitions and manage the staging, a low-cost standalone printed circuit board, or PCB, is integrated into the system, acting as the brain of the phase staging sequence. This PCB not only manages the staging sequence, but also prevents staging should the buoy be dropped from a low altitude. Finally, phase was designed to match the existing legacy sonobuoy form factor, and all added components required for phase fit seamlessly into the current A-size legacy buoy. Phase is currently under development in a Phase 2.5 contract that is set to complete in the second quarter of fiscal year 2024. There are 4 primary goals of this 2-year contract. The first goal is to prove the reliability of the phase system when integrated into production sonobuoys, and collect ballistics data to feed aircraft software. The most recent airdrop revealed a 75% success rate, which is the highest seen since the phase system has been introduced to the more vigorous flight environments of multi-mission aircraft. SeaLandAir believes that achieving near 100% reliability before the end of this contract is well within reach, and the majority of our efforts will be put towards accomplishing this goal. In parallel to the reliability effort, the airdrops have allowed the phase team to collect aerodynamic ballistics information of phase-equipped sonobuoys that will eventually feed multi-mission aircraft software. The second goal is to evaluate the price of a phase module, in order to shed light on the additional costs that would be required to procure phase-equipped sonobuoys. To accomplish this, SeaLandAir has partnered with a prime sonobuoy manufacturer to conduct a cost assessment of the phase module and determine the cost delta between a legacy sonobuoy and a phase-equipped sonobuoy. The third goal is to investigate the phase system as it relates to hazards of electromagnetic radiation ordnance, or HERO. In this contract, a HERO test will be conducted to determine where the specific areas of susceptibility are and potentially follow by integrating HERO damage countermeasures. The fourth and final goal of this contract is to draft and deliver proposed updates to the production sonobuoy specification, or PSS, that will accommodate phase-equipped sonobuoys. These changes focus specifically on phase decelerator specifications, including geometry, drag area, and ballistic coefficient, as well as staging definition and altitude limits. The key features and advantages of phase can be summed under one statement: added performance capability with negligible impact on current sonobuoy size, weight, and power. This means a product that will improve Navy capabilities without added stipulation to current sonobuoy storage, handling, and usage. As has been discussed, the primary performance benefit of phase is the reduction of sonobuoy time to splash and consequentially improved accuracy. The charts below describe the improvement for time to splash both for the die-cast and die-fire sonobuoys. As can be seen, phase effectiveness is maximized as drop altitude is maximized. In other words, the higher you drop a phase-equipped sonobuoy, the more substantial the gains in time to splash reduction. Coupled with the performance benefits are negligible effects on sonobuoy size, weight, and power. As previously discussed, phase was designed to seamlessly integrate into the A-size sonobuoy form factor. In other words, when packaged, a phase-equipped sonobuoy and a legacy sonobuoy are identical. On top of that, they weigh virtually the same, with a weight difference that is on the order of grams. Additionally, a focus was maintained to pursue solutions via simple, low-cost parts and assemblies, thus minimizing the cost to purchase and produce. Therefore, the current cost delta estimate between a phase-equipped sonobuoy and a legacy sonobuoy is at a modest $40 difference, though further clarity is still to be obtained on this subject. With phase being in the latter readiness level stages, the goals of the current contract and goals to transition to the fleet are the same. As mentioned previously, there are 4 primary goals SeaLandAir is striving towards. First, we are working to prove out the reliability of the technology when deployed from an MMA platform. Secondly, we are working with a prime contractor to perform assessments and to develop recommendations for cost reduction to ensure minimal impact to current acquisition programs for these expendable devices. Third, we intend to conduct a HERO evaluation and, if time allows, adjust the design to qualify the phase module as HERO safe. And fourth, we intend to draft and deliver recommended updates to the PSS in order to smooth phase integration into the fleet. Our primary advocate in this work is the Naval Air Warfare Center Aircraft Division, or NOCAD's, PMA 264 and PMA 290 offices. As mentioned earlier, subject to funding availability and Navy warfighter requirements, we anticipate completion of these goals as early as the second quarter of fiscal year 2024. The present SeaLandAir market analysis indicates that sonobuoy prime manufacturers are focused on producing units to spec while maintaining adequate profitability. The primary driver for SeaLandAir is to maintain a strong relationship with NOCAD and continue to work toward adding phase to the PSS and subsequently included in future production manufacturing of die-cast and die-fire sonobuoys. Additionally, it is believed that phase could be incorporated into any NavAir sonobuoy or air-released asset. Beyond NavAir capabilities, we believe this technology would also be beneficial for other military airdrop applications, including airborne logistics, search and rescue, and humanitarian aid delivery. Imagine soldiers hiding in high-risk war zones with little to no option of leaving shelter, and airdropped care packages can be delivered from high altitude with minimal detection. Or maybe towns and villages receiving aid from high-altitude aircraft with no alert to oppressing governing bodies. Phase would allow for airdropped packages to be delivered in stealth with speed and accuracy. Outside of military applications, phase could also be incorporated into commercial applications such as drone deliveries, medical supply delivery, and firefighter support. Commercialization beyond the sonobuoy industry will be SLA's focus once full incorporation by prime manufacturing partners for NavAir sonobuoys is complete. The transition plan for the phase module technology is principally targeted towards sonobuoy applications. Phase-equipped sonobuoys are currently undergoing testing from MMA platforms to validate the reliability of the system and collect valuable ballistic information. Following this testing, NavAir will add a specification for the phase-equipped sonobuoys to the production sonobuoy spec. It is anticipated that this process will be executed smoothly, as drafts of this spec change have already been developed between the SeaLandAir and PMA-264 teams. With the reliability of the design validated and a spec change in place, phase-equipped sonobuoys can then be ordered and procured for Navy use. The plan for secondary applications begins with research and consultation into how phase can be scaled for use in larger applications and transferred to manufacturers. With the concept and goal of this technology to primarily benefit military defense applications, it is expected that a comprehensive transition evaluation will be required to grease the skids on a technology transfer to the public sector. As can be expected, any technology instructions or training documents will be evaluated throughout the transition. Well, thank you for taking the time to listen to this presentation today. I hope that you have gained a better understanding of the phase program on what it is, where it's going, and what it's capable of. For further information, please feel free to contact me, Win Curry, the project engineer on this program. Additional contacts such as James Dodge, Senior Program Manager, or Miles Woodard, Director of SeaLandAir Business Development, can also provide comprehensive background, material, and answers to any questions that you may have. Thank you so much for your time today, and we look forward to speaking with you.